So, this is VCM plus VD, VCM minus VD. We found the operating point, right, and therefore, now we are ready to do small signal analysis. Of course, the easiest thing to do is simply replace every transistor with its incremental equivalent and then go and do the math, right. However, we can do something smarter here, and what enables, I mean, I am going to claim that we can do things in a much simpler manner, and what we have discussed so far, namely simply blindly going and replacing every transistor with its incremental equivalent works. There is nothing wrong with that, but one thing we are not exploiting that would work for any circuit. In this circuit, there is also something special that we have not exploited, and what is that we have not exploited? When you stare at the picture, it is symmetric. So, whenever there is symmetry in a circuit or whenever there is symmetry in anything, you can always exploit it to simplify analysis, right, and break it up into simpler problems, right, and that is we will use symmetry to simplify our lives, okay. And so, that clearly the circuit is symmetric, and so in the small signal equivalent, what happens if we draw the small signal equivalent, what happens to VDD? Grounded. Capital VCM goes away, this becomes minus VDD. What happens to 2I0? The 2I0 is often also called the tail current source, okay. All right, and so this is the small signal equivalent, where now the transistors are assumed to be are representations of their small signal equivalent circuits. Now, we need to analyze this. So, we see that there is an axis of symmetry, okay, and whenever there is an axis of symmetry, you can always simplify life, right, and let me illustrate. So, let us say you have a circuit like this, some arbitrary linear circuit, okay, and you let us say there is a copy and paste of that one here. So, this is exactly equivalent. So, let us say we have a node A here and a node the correspond, I mean, this is an axis of symmetry, the circuits are not connected at this point, two identical circuits, okay. Let us say we excite one with Vi, the other one with minus Vi. Alright, so this is, let us say this is ground. So, what comment can you make about the voltage, small signal voltage Va on the left side versus the right side? The polarities on the is the same circuit, linear circuit excited with negative of the excitation. So, therefore, by linearity the voltages at the corresponding nodes in the left and the right will be exactly identical in amplitude, but 180 degrees in phase, correct. Okay. So, what comment can I okay, if I now join this node to that node, what comment can I make about that voltage? So, if you look at the Thevenin equivalent at point A, what will the Thevenin equivalent be for the circuit on the left? Come on, quick people, there will be some. So, basically there will be some VA and some in series with RTH. For the circuit on the right, it will be RTH and minus VA, and therefore, when you join these two, that voltage will be 0. So, it is not merely enough if simply the polarities of the two voltages are equal and opposite, right. The polarities are opposite and the magnitudes are equal. It must all, it is also important that both the Thevenin impedances are exactly the same. You understand? So, because the circuits are because of symmetry, the circuits are exactly identical, and therefore, the Thevenin equivalent is the same, and therefore, if you join these two nodes, the net voltage, the voltage at the middle will be 0. Okay. So, so now let us see. So, this is what I will call the differential mode analysis. And to do that, we recognize that there is an axis of symmetry, the two sides are being excited by equal and opposite voltages. So, this node, what will be the, based on our discussion just now, what comment can we make about that common source node? Why is it called common source node? The source is common to both sides. So, what comment can we make about the incremental voltage at the common source node? It will be 0. Okay. If that is 0, and what comment can you make about say let us call this VO1 and VO2? They will be equal and opposite. So, there is no point in solving the left side and the right side, you can only solve one side, and the other, the voltages on the other side will be simply be the negative of this. So, we can only therefore work with half of the entire circuit, and since this half came with due to differential mode analysis, this is called the differential mode half circuit. What should I do to the source? Therefore, source must be ground. So, how does this look? I mean, this is very familiar. This is nothing but the common source amplifier. So, VO1 must be minus GM R times VD. All right. What is VO2 therefore? Plus GMR times VD. So, basically this is the incremental voltage is GMR times VD. This is minus GMR times VD. Sorry, minus GM, this is plus. Correct? All right. Now, let us say, remember when we derived the circuit, we said that our circuit only responds to it only responds to the difference between Vx and Vy. It does not respond if Vx and Vy change by the same amount. In other words, if the common mode changes by some amount, the output should not change. So, like, I mean, we should verify that fact, correct? And to verify it, again, what should we do? This was VCM. If the differential mode was 0, this was let us just simply VCM on both sides. So, how do we verify the fact that our outputs here VO1 and VO2 do not change if both the inputs are changed by the same amount? How will we verify it? Yeah. So, basically we apply a small change, we move both these sides up by the same amount, and and check to see what VO1 and VO2 are, right. What will we find or what should we find? Let me rephrase the question again. The output, which are our outputs? Either VO1 or VO2, depending on whether we want positive polarity or negative polarity, any one. Let's say VO1. Okay. When we started off, we said that this VO1 must only depend on the difference between Vx and Vy, correct, which corresponds to the differential mode part of the signal, and it should not depend on the common mode voltage, right, and we are trying to verify that using analysis, correct. So, to that end, what are we doing? We are keeping the differential mode 0, correct, do you understand? Okay, and we are increasing both Vx and Vy by the same amount, alright, and the question I am asking you people is, what should we expect to find for VO1? We should expect to find 0 because the output is not expected to depend on any change in the common mode. Is this clear, people? Alright. Now, so therefore, we now are expected to do analysis of this circuit, except that now both sides are pushed up by the same amount, alright. So, again we exploit symmetry. The circuit is absolutely symmetric about this point, correct. So, if we draw the circuit now, it is basically so what are we doing? We are taking two identical networks. We are now we are applying the same potential Vi to both sides, okay, and let us say you connect, let us say there was a connection like this. What comment can you make about the connection? What comment can we make about the current through that connection? 0, right, and why? Because, well, by symmetry, VA will be the same as VA on the other side, and therefore, no current can flow, and therefore, this can be no current can flow, you can remove that connection, right. No current flows for any value of Vi. So, you remove that connection, and therefore, you can only analyze 1/2. On the other side, you get exactly the same. So, so that is now again half circuit analysis, but now it is coming for common mode excitation. So, that half circuit is called the, what will you call it? The common mode half circuit, correct. So, what will you do with VDD? What should we do? Ground as usual, okay. Current source, open circuit, and then we can forget about what happens to this wire. That is the one which is connecting both the halves, correct. So, this can be removed. So, this incremental VO1 is what we are interested in finding. Is clear, people? Alright. So, this circuit is also familiar to us. So, what is the incremental, and this VCM, capital VCM goes away, this is only small VCM. So, what comment can you make? Why? Well, there is no source resistance. So, So, what comment can you make about Vy there, small signal Vy, alright. So, VO1 must be equal to 0. So, what comment can you make about VO2? That is also 0. So, this confirms our original what do you call hypothesis when we derived the circuit, that such a circuit would only be dependent on the difference between Vx and V1, alright. But of course, there is I mean there is the practical non-idealities. So, we assumed that this current source is ideal in our analysis. As we have seen here, the current source is not, is often realized by using some kind of current mirror, correct. So, what will be the small signal equivalent of this current source? In practice, that small signal, that this what do you call, this is not really going to be an open circuit. It is going to be, let me, so common mode gain the common mode gain is nothing but 0. The differential mode gain is nothing but minus GMR, alright. Okay. So, in practice, the resistor, this is going to be some current source, right. So, this is capital VCM plus small VCM, capital VCM plus small VCM, and this is R, correct. So, in the incremental network, what should we replace? VDD of course will be grounded, very good. What should we replace the tail current source by? Yeah, some let us call this some RO, right, which is the output resistance of that current source. Okay, if you want to make a better current source, what will we do? What will we replace that transistor, single transistor by? Yeah, you have to use a cascaded current source which increases the output resistance by a factor GMR. So, anyway, whatever that output resistance is, it is okay. Let us call that capital RO to stand for appropriately. You can so now to analyze this, again we see symmetry and we want to find out what this VO1 is. So, what comment can you make? How will we analyze this circuit? Can we exploit half circuit analysis? Okay, well then yes, I remember that half circuit analysis means that we have two identical circuits and we have something going from one side to another. So, this you can always split as 2R0 in parallel with 2R0 and the half circuit basically analysis basically means that you get rid of this half okay. So, what comment can you make about VO1? What is this incremental voltage? Now, you should be able to tell me quickly. Very good, it is GM times 2 GM R naught by 1 plus 2 GM R naught, very good. So, what is the current flowing there? That is just this divided by 2 R naught. So, basically, and what comment can we make about GM R naught? Is it a small number or a large number? It is a large number. So, what comment can we make about this quantity? Yeah, that is roughly 2 GM R naught. So, what comment can you make about this whole expression? This is approximately VCM. So, what current can you will flow through the transistor? VCM by 2 R naught, very good. What comment can you make about the incremental voltage there? Therefore, VO1 minus R over 2 R naught times small VC. Okay. So, if the tail current source, so what is the bottom line? I mean, okay, this is the analysis. So, what does this mean? What is this telling us? So, ideally, we were hoping if the current source was ideal, the differential pair, the output of the differential amplifier would only depend on the difference between the two inputs Vx and Vy, right, with no dependence on the common mode component whatsoever, right. Unfortunately, in practice, the current source is going to have a finite output impedance. We do know how to make the impedance better, but it will always remain finite, okay. And the consequence of that finite impedance is that the gain for common mode signals is not 0, all right. It is this quantity, minus R by 2 R naught, and if and what is this is ideally supposed to be 0, but it is not 0. I mean, see, one thing you must realize that in life and in engineering, nothing that is supposed to be 0 will be 0, nothing that is supposed to be infinity will be infinity, right. Okay. So, so the common mode gain in practice therefore will be VO common mode gain, which is ideally supposed to be 0, will be now by 2 R naught, okay. And recall what is the differential mode gain? Or the differential gain is minus GM R, right. So, this is often called ACM for common mode, and this is ADM for differential mode. So, the ratio of the differential mode gain to the common mode gain is, which ideally should have been infinite. It should not have responded to common mode signals at all, right. Unfortunately, because the current source is not ideal, this common mode rejection ratio CMRR common mode rejection ratio will be which is ideally supposed to be infinite, will be nothing but 2 GM, and this R naught is the output resistance of the tail current source. So, again we see that nothing in the world which is supposed to be infinite will be infinite. So, that gain, that common mode rejection ratio which was supposed to be infinite is not quite infinite. We only hope is that it can be a large number, right. If you use a Sida Sada current source, right, with an output resistance of RO, then this will be of the common mode rejection will be of the order of GMRO. If GMRO is say 50, then the common mode rejection is it's 100, but yeah, it's roughly of the same order, correct. Now, if you put a cascaded current source, what comment can you make about the common mode rejection ratio? It will be of the order of GMRO the whole square, correct, and so on. So, to summarize the properties of the differential pair, is 2I naught, and that is, let us assume that has an output resistance of the input voltage is capital VCM plus some small VCM plus some small VD, okay, where the small VCM models the change in the average voltage, this is minus VD, that is R, that is R, that is VDD, VO1, VO2. So, the small signal, the quiescent voltage at node, let us call this A and B and X. So, the quiescent voltage at X is what? VCM minus VT minus some overdrive delta V, and what is delta V? Yeah, it is nothing but square root of 2 I naught over mu n C ox W by. Okay. All right. So, the incremental voltage at X is what? What will be the incremental voltage at Vx? It is simply, how did you get VCM? So, I mean, what do we do? Well, again we go back to symmetry, we find the individual voltages, right, and when you put both of them, I mean, so you can think of this as the following. If you want to analyze what happens when there is a common mode change as well as a differential mode change, simply by superposition you can consider only the common mode first, only the differential mode next, and use superposition to add up the potentials that you get in both half circuits, right. So, basically in the differential mode half circuit, what comment did we make about that node X? 0. In the common mode half circuit, what did we? Approximately VCM, because the incremental gain was 1. So, what comment can we make in the total circuit? Small Vx therefore is Vc, small Vc. All right. All right. At nodes A and B, what are the quiescent voltages? So, let me make write the quiescent voltage at node A, VDD minus I naught times R, which is the same as the quiescent node voltage at node B. Okay. And what comment can we make about the incremental voltage at node A, which is what we call VO1, which is again it is the sum of the voltage due to common mode excitation and the voltage due to differential mode excitation. So, in the common mode half circuit VA was minus capital R by R naught by 2 R naught times small VCM, and what is the differential voltage? Minus GM R VD. Okay. What about small VB, therefore, without just closing your eyes, and the common mode voltage will be the same, plus that makes sense, folks. So, this is all that there is to the differential pair with resistive load. The gain that you can get, therefore, is if you take either VO1 or VO2, the gain that you get is basically for the differential. I mean, remember that the difference between Vx and Vy is, what is the difference between Vx and Vy? 2 Vd. So, the output voltage VO2, for example, is nothing but Gm times R times by 2 times 2 Vd, right. So, the differential pair is therefore giving you a gain of GMR by 2 for the difference between the terminals Vx and Vy. Okay. So, this is this is basically doing the job of a common source amplifier, except that it is attempting to only amplify the difference between Vx and Vy without ideally reacting to the common mode component. In other words, if Vx and Vy change by the same amount, ideally the differential pair output is not supposed to react to the change. However, in practice there will be a small change due to the common mode component, right. So, ideally to see what is coming next, this gain GM R by 2, of course, is can't be very large, right. So, just like how in a common source amplifier you cannot make that GMR, if you attempt to if you make that load resistance very large, what comment can we make? For a given supply voltage, as you keep making R larger and larger, you will eventually end up, you can't get too greedy. Eventually the transistor will go into the triode region, correct. And the only way to fix that problem was, if you wanted to keep a resistive load, you had to keep increasing the power supply voltage. Here, again here also we see the same problem. If you want to get more gain by keeping while keeping the transistors and 2 I naught, the tail current source, the same, what will you do? The formula tells us that it is Gm times R by 2. So, you go on increasing R. So, what happens as you go on increasing R? The transistors will eventually move into the triode region, right. Okay, and the only way to fix that problem is to keep increasing the supply voltage, right, and to increase the gain by a factor of 100, you would have to increase the supply voltage also roughly by the same factor. So, what was the fix for that problem earlier? Yeah, so we used an active load. So, the same thing we will do here. Does it make sense? Right. So, we will take a look at that is the motivation for trying to introduce the active load, it is very similar to what we did for the common source amplifier. And tomorrow we will take a look at the how we enhance the gain of the differential pair with an active load. Thank you very much.